All right, so this is a problem like number 9 from problem set 14. But we are going to do the problem number 2 on page 515. Now, I would recommend that you do this problem on a separate piece of paper because it does take up a lot of room, a lot more room than what is given. So page 515, number 2. And like I said, this is like number 9 on problem set 14. So you've got a lot going on in this problem. We've got CSOH plus HCl yielding CSCl plus H2O. What type of reaction is this? Yeah, this is an acid base. So what happens in an acid base if you have a relatively large quantity or a high molarity, you're going to get a noticeable temperature difference. Now that will allow us to calculate a delta H of the reaction. So we will go ahead and start. Let's list our givens. Our CSOH temperature before mixing in both solutions. First, let's get the above the reaction. Assume you mix 100 milliliters of 0.2 molar CSOH with 50 milliliters of HCl, and that is 4 molar. Temperature initial of both solutions is 22.50 degrees Celsius. And it rises to 24.28 degrees Celsius. What is the enthalpy change for the reaction per mole of CSOH? I'm going to change this to HCl, and you'll see why in a little bit. But we can do CSOH. It's just going to be different than your answer. So assume the volumes are additive, the densities of solution are 1 gram per milliliter, and the specific heat capacities are 4.2. I'm going to change that 4.2 joules per gram Kelvin. The specific heat capacity The density is the density of H2O, which is 1 gram per milliliter, because it's a very low molarity. So you're just going to go ahead and assume that the solutions that are dissolved in water and diluted in water is 1 gram per milliliter. That means the heat capacity is 4.184 joules per gram Kelvin. It's going to change our number from our answer. Well, our answer is going to be vastly different. But I know that my process is right because I checked with my friend that teaches chemistry from NKU. All right. So we are going to use Q of the system equals mass of the system times the heat capacity of the system, which is all water. So that would be the heat capacity of H2O times delta T of the system. Now we need a mass. We need a mass of the system. The system is the reaction itself, the two solutions. So the mass of the system is going to be the mass of the CSOH plus the mass of the HCl. That's where the density comes in, right? If we have 1 gram per milliliter for the density of the solutions, we can say that the volume is going to equal the mass, right? So the mass of the system is 100 grams of CSOH plus the 50 grams of the HCl. So your mass of your system is 150 grams. Like I said, the system is the reaction, so we can say Q of the reaction equals mass of the reaction times the heat capacity of the reaction times delta T of the reaction. So we can go ahead and calculate heat of reaction. We have the mass of 150. We have the heat capacity, which is 4.184. And we have delta T. Now, one thing that I have taught with delta T is that you change to Kelvin, but I don't know if you have realized that you subtract out the 273. So you can go ahead and plug in the Celsius temperature for delta T. It is most precise, and that's why I taught it to convert to Kelvin. But you don't necessarily have to if you don't want to, as long as you have both temperature final and temperature initial. So we can go ahead and calculate a number. We get 1,117.128 joules. Might as well convert that to kilojoules, which is 1.117128 kilojoules. Now we're going to use our heat capacity knowledge or our heat of reaction, we know that the heat of the reaction is the negative heat of the surroundings. So the heat of the surroundings is negative 1.117 kilojoules. So this is the first step. It's just what we call calorimetry. First is just standard calorimetry. It's what we've been doing. Next is a little bit different. We still have not calculated what we want. We want the enthalpy change for the reaction and mole of HCl, but the mole of reaction is the same as the mole of HCl. And the same thing, the mole of the reaction is the same as the mole of CSOH because all of our coefficients are 1. So if we find delta H of the reaction, we also find delta H per mole of each of the reactants because they're all 1. The mole ratio is 1. So is it okay if I erase almost? All right. I want to remind you that Q of surroundings is negative 1.17 kilojoules. Where is it? 117. 117. All right, now you do reaction stoichiometry. Limiting reactant. So we have a volume and a molarity. We can calculate the moles of product produced. So you have 0.1 liters of CSOH times the molarity, which is 0.200 molar CSOH. And that's over, sorry, that should be moles over 1 liter of CSOH. That cancels out my liters. Now, we can get away with not calculating the grams of product because we can calculate moles. We can stop at moles because the least amount of moles will produce the least amount of grams. So we might as well save our work because the work is very daunting for this problem. So we have 1 mole of CSCl for 1 mole of CSOH. So we get 0.02 moles of CSCl. For HCl, we get 0.05 liters of HCl times the molarity, which is 0.400 moles of HCl per 1 liter of HCl. That cancels out my liters. And then for completeness, 1 mole of CSCl per 1 mole of HCl. And that gives us 0.002 moles CSCl. So which reactant was the limiting reactant? The HCl was limiting. So you're going to use the moles of HCl and to find delta H. So delta H is the surroundings because that's what we want over the moles of HCl. So you get negative 1.117128 kilojoules over. Now, if you understand the math, the 0.002 is the moles of HCl, right? Because the last step is multiplying by 1/1, which that's meaningless, but you have to show it in order to be complete with the chemistry. So we have 0.002 moles HCl. Therefore, our delta H is going to be negative 559 kilojoules per mole HCl. Now, if you wanted moles of CSOH, you would just do, again, enthalpy stoichiometry. And do your negative 559 kilojoules per mole HCl times your 1 mole HCl. This is your mole ratio. and this is over 1, over your 1 mole of CSOH. And that would cancel out your moles of HCl because one's on the bottom, one's on the top. And you get negative 559 kilojoules per mole CSOH. So the key for this is wrong. I do know that this is right because I sent a picture to my professor friend, and he's one of the smartest people I know in chemistry. And he said that this is indeed right. So basically the key points for this is the first step is finding the total mass, right? You find that using the density. If it's water-based solutions, which all solutions are, the density you can assume to be 1 gram per milliliter. That means that your volume that you're given is the same as your mass. You need a total mass for the reaction, okay, because conservation of mass. You take your mass of each reactant and add them together. That gives you the mass of the reaction. Then you can use Q equals MC delta T to find the heat of reaction. Then you flip the sign because you want the surroundings. So the heat of the surroundings is going to be the opposite sign of the heat of the reaction. And then you do this. You do reaction stoichiometry where you're finding the limiting reactant, which we're all good at there. And then you're going to take the least amount of moles. That's going to be your limiting reactant. And then you're going to use your moles of your limiting reactant and do Q of surroundings divided by the moles of the limiting reactant to find the moles of what you're interested in. Now, if you are asked for the opposite reactant, the excess reactant, all you have to do is heat stoichiometry, enthalpy stoichiometry, where you use the mole ratio to find the heat given off by the other reactant. So that's this. And like I said, your key is wrong. They didn't do limiting reactant to make the key. But this is what you want to do. So are there any questions? It's a lot, isn't it? Yeah. But yeah, so and that's why I didn't do problem 9. We had this problem in our guided notes, so we might as well have used this problem. The only different thing is that number 9 from problem set 14 has the mole ratios are not 1:1, so you have to watch that. So your moles, what I would do is separate these 2 steps. That way you have a mole of your reactant, but you still got to go to this second step. But you would save a calculation if you separate the two steps out in the different parts. But this one, it was 1-to-1, so when you get the moles of your reactant, you also get the moles of your product. I'm going to upload this video. I uploaded the other video. I'm pretty sure everybody has access to it. I'm going to upload this video, so if you forget how to do this problem, you always have access to it. This problem is based on lab, so we are going to do a lab over this problem. So your calculations will be identical to this. And it is a neutralization reaction too. And it will be 1-to-1 mole ratios. But I'm going to change, you're not going to be given the same molarity